measurement of the gamma angle was presented a few days ago at Beauty for the first time, and it exploits with a quite complicated analysis the old dear Dulles plot, which is a very interesting and sensitive way to access information on hadronic decays. You can divide this plot in several regions and extract the parameters that give you access to gamma, and you get this new measurement, which is the most precise single determination of the angle. But most interesting is the fact that you can combine these two measurements and many, many others into a single value of gamma, and the error is becoming very, very interesting. So we are at the level of 5 degrees already, and this is the world average. So you can see that who is dominating the world average, actually. And as I said before, so this is the direct determination, but if you in the flavor sector, you can get an indirect constraint on the gamma angle, which is 65 degrees. So there is a slight tension between the two measurements. Of course, there's nothing to get too excited, but it is worth to keep an eye on that. And especially, it demonstrates you that it is very worth to measure precisely these kind of parameters. I will come on this towards the end of my presentation. Of course, I cannot avoid saying a few things on lepton flavor universality violation, because even though these are not new measurements, this is somewhat a hot topic. So as you know, we can test the lepton flavor universality, which means that you check whether the standard model is blind with respect to lepton flavor. So if the amplitudes and decay rates are the same for all the leptons except for kinematic factors. And you can build several observables made of ratios of branching fractions, like, for example, in this case, semi-tawonic decays into semi-leptonic decays in 2000 muons of the D star meson, of the B meson, or the decays into K star or K to mu mu and K to E, and where you have a quite clean theoretical prediction, especially because many factors where you have uncertainty cancel in these ratios. So you measure these ratios, and also the measurement is quite precise because you can cancel a lot of systematic errors. And we get, for example, for the family of the RD or RD star measurements, which are semi-leptonic decays, we have a collection of measurements not only from LHCb but also from the B-factory experiments, Babar and Bell. And you see that this is the combined measurement world average, and this is the prediction of the standard model. So there is quite a tension here, although not coming from a single measurement, but from many different measurements combined. So this is an interesting thing to look at. And the other interesting measurements that were made by LHCb and also originally also from the B factories is the RK ratio of branching fractions, and you see that the latest measurement of LHCb for RK is away from the standard model prediction, which is essentially 1 by some 2 sigmas, and in the two beams of transfer momentum for the RK star observable, we have discrepancies between with respect to the standard model predictions at the level of 2 to 2.5 sigmas. We are updating the measurements, and the analysis is very complex, so the update will come sometimes in summer or early fall. But there is potential to have a confirmation of these results at the level of 4 or even 5 sigmas, and provided, of course, that the central value will stay there, or otherwise we can see that it was just a statistical fluctuation, and the standard model will win again and again. So something to take under observation. But of course, this is a broad sector of physics, precision physics, that we do at LHCb. But of course, there is a huge amount of other measurements that we do, like, for example, studies for what concern quarkonium production, which is very interesting to test QCD and many other hadronic physics models. And I'm quoting here a few measurements concerning the production of upsilon mesons. Essentially, these also provide sort of standard candles for our experiment, because we can measure very precise branching fractions and production cross-section and test how well our detectors and how well we control our systematics. So I don't go into the details, but just to show here the beautiful upsilon resonances peaks that we reconstruct in our experiment. This is made with a small amount of data at 13 TeV, and we can get a lot of interesting and precise results on differential cross sections and so on. I think that later on Valeria will present something about these studies, namely on charmonia, which is a similar technique and similar studies to this. Also, for what concerns particle production, I want to stress that we can do also high PT physics at LHCb, in particular studying the production of particles and jets in the forward direction, which is a region, phase space region, which is not covered by ATLAS and CMS. So it's a complementary phase space region that we can probe. In particular, this is an interesting result on top pair production in our detector. And the two top quarks are identified through their leptonic decays. And as you can see, we have a very pure sample here. It's this purple area of the histogram. And we can measure the cross-section in the fiducial area covered by LHCb. And we are still statistically limited, indeed, because for us it's certainly is not an easy channel to do. But we certainly, with the upgrade and with the end of round 2, we can reduce substantially these statistical errors. So it's a kind of physics which was not considered core program in our experiment, but it's still very interesting and complementary to ATLAS and CMS. We are not doing only flavor physics, but we have also a very important heavy ion and fixed target physics, because LHCb can work in 3 different ways. In collider mode, where we can collide protons or protons against nuclei or nuclei against nuclei, or in fixed target mode, because we are able to inject gas inside the vacuum pipe in the region covered by our vertex detector. And we can inject, for example, helium, neon, argon, and so we can do very interesting measurements for heavy ions, for example, colliding protons on these gas targets, or even ions on these gas targets. And we can do very interesting measurements comparing the cross-sections or production mechanisms with different nuclei species, which is very unique at LHC, sorry. And this, of course, is a very interesting and inspiring setup. And in fact, there are, I think, 3 talks in this session by Valerie, Vasil, and Vladimir about possible applications of this setup for other physics applications and studies. So this was just a quick glance of a few things that we can do at LHCb and a few recent results. A few words now to the LHCb upgrade, which we are building and we are going to install in the next few years. So the LHCb upgrade essentially is based on the fact that we want to rise by a factor of 5 our instantaneous luminosity, so we go to 2 × 10⁻33, and we want to have a fully software trigger, so a trigger that is able to digest events at 30 megahertz input rate, and reconstruct and filter every single collision. In this way, we can reach huge increases in efficiency, especially for the fully hadronic final state channels. So this is clearly a challenge and required to reconstruct, redesign, and rebuild all the tracking detectors, namely the pixel detector, the silicon tracking stations upstream the magnet, and the tracking stations downstream the magnet, redo the photon detectors for the Cherenkov particle identification detectors, and redo the readout electronics for the calorimeters and the muon system. And of course, to rethink completely the trigger, which is now completely software. There is no any hardware filter in our experiments. So just a few slides about the upgraded detector. So this is a snapshot of the Velo, which is built of silicon pixel modules on a silicon microchannel substrate. So you can see here a sort of radiography of the plates where you can see the microchannels where the CO2 is flowing to cool these modules, and here you can see one of the modules under construction. They are quite complex devices, and then this is a picture of the silicon tracking stations, which are made of these long so-called staves, so supporting structure with several silicon sensors aligned. And here you can see one of those sensors and part of here in particular the construction of the supporting structures of the staves, which is going on in the United States. For the tracker, we have a large scintillating fiber detector. So we have these are long 2.5 meters long modules made of a lot of tiny scintillating fibers, 250 microns diameter. And in fact, we needed 12,000 kilometers of scintillating fibers to equip this detector. So it's quite an amazing number. The construction is progressing quite well, and here you already see the assembly structures, and we are cutting the walls of our building to let this big detector enter into the pit. So it's quite a heavy activity there also. And finally, for what concerns the particle identification detectors, as I said, we have to build the new photosensors, which are photodetectors, which are multi-anode photomultipliers, and for the muons, we are reconstructing, fully reconstructing the readout electronics, and for the calorimeters as well, we had to redo the readout electronics to comply to the 40 megahertz readout rate. And finally, a couple of words about the trigger, which is the real challenge of our experiment. So processing data at 30 megahertz is not a joke. So we need a heavy software modernization. We need proper software engineering, and exploit modern CPU features like multi-threading, vectorization, etc. So there is a huge effort ongoing in this area, which is to me most probably the most exciting and challenging development in particle physics now. And okay, here I'm showing, for example, here the huge gain you have going to multi-threading and vectorialization process. So this is the number that you are able to process per second per node, and you start from essentially 1,000 and you can go up to 12,000 using these modern techniques. But there is still a lot to do here in the next few years. So I look to the far future. In particular, we are considering for LHCb to make a a second upgrade in a time scale of the HL-LHC that was presented this morning, because we believe that we have to provide a very high luminosity flavor experiment for the ultimate exploitation of LHC for flavor physics. So this is the timeline we are considering. So now we are here in 2018, and we are approaching the long shutdown 2, where we will install the first upgrade. Then we will have a run 3 and run 4, where we will run this first upgrade in competition with Bell 2, which is starting now to take data, is commissioning. But then after run 4, so for run 5 and run 6, there will be essentially no planned flavor physics experiment. And so we think that it will be extremely important that we can cover this running period with a dedicated experiment. So clearly, this is a challenge. We aim at a flavor experiment running at 2 × 10⁻34 of luminosity with 55 visible interactions per crossing. So it means that we will have 55 primary vertices, which is a challenge for a flavor experiment where you want to reconstruct the primary and secondary vertices and measure decay length, etc. And also from the detector point of view, is very challenging. We'll have a lot of tracks, a large occupancy that will challenge our particle identification systems. And also radiation damage will be substantial also for the calorimeters, but especially for the vertex detectors, which is our vertex detector is essentially inside the beam, is 5 millimeter away from the beam line, so it will be severely affected by radiation damage. And then, of course, we will have so many data that to process that this will be really a big challenge, how to cope with this flood of data. There are some ideas that are sketched here, but still at the level of R&D and brainstorming. So some challenging, some new modern pixel detectors, etc., etc. And some ideas also for a new calorimeter where we have to use fast and radiation hard scintillators. We saw many ideas here already today, and so this is something that can be of interest also for you. And also other techniques that are studied for this calorimeter, which is will be one of the most important elements of this second upgrade. And of course, as I mentioned, the data handling and the computing will be the problem for this experiment, but also please notice also for Atlas and CMS phase 2 upgrade, because I don't know how they will handle the large amount of data that they are planning to collect. I'm concluding with this. Why a super high luminosity flavor physics experiment? Well, you can see here, for example, if you take the precision on the gamma angle, and after the upgrade 1, we will have a precision approaching 1 degree, and after the second upgrade, where we plan to collect 300 in Vance Fermtovarn, we should go down to 0.3, 0.2, 0.3 degrees. And this is the scenario that eventually we will have after the second upgrade and the Bell 2 contribution. And if you take this picture and you put it on the standard unitarity triangle, you may end up in a dream scenario like this, where the triangle is not anymore a triangle, but there is clearly a lot of new physics to be explained here. It can be a dream scenario, it can be a realistic scenario. Let's see what happens. So, but this just tells you that it is really worth to measure very precisely these parameters. Okay, this is my last slide. So to conclude, LSEV, this will be the last year of LSEV. We took a lot of very interesting data. We produced a lot of beautiful physics. We are starting the marathon to install our first upgrade during the LS2, but we are also looking into the far future, and I think that there are a lot of opportunities for hardware groups and physics group to take for us and to join us for the future upgrades. Okay, thank you very much.
Questions, please. Okay, questions, please.
My question is in fixed target. So when you operate in fixed target mode, if there is technical possibility to use all possibilities of detectors, or because some problem maybe not.
Yeah, no. Yes, absolutely. So the only difficulty is that the gas expands at the moment. The gas expands into the windpipe down upstream up to 20 meters upstream. So there are collisions that occur quite upstream with respect to our vertex detector. And so the efficiency to reconstruct these collisions is very small. So it drops quite quickly when you go upstream. Essentially, at 1 meter upstream, the vertex detector, you are not able anymore to reconstruct the primary vertices. So this is the only difficulty. But we are planning to upgrade this system with a storage cell, which will be inserted inside the vertex detector. So the gas will be much more confined in this way. And so the vertices are essentially at the same place where the two proton beam collide in normal operations. The storage cell allows us also to potentially inject also more fancy gases like oxygen or hydrogen, or for example, for studies of cosmic rays collisions into the atmosphere, etc. So this is an upgrade that we are studying, and if there are no showstoppers, we will try to install it. Yeah.
Ask the questions, please. Let me ask you. Yeah, okay.
No, sorry, you don't want to.
Which is the maximum significance of the deviations from the standard model with the CB can see now at the moment?
With this, sorry?
Which is the maximum significance of the deviations of the standard model of the CB now?
Yeah, so you mean for the lepton flavor violation, yeah. Lepton universality violation. Yeah, so at the moment we are at the level of the maximum deviation is 2.5 sigmas, which is still within possible statistical fluctuation, of course. The thing that makes this interesting is the fact that there are many different measurements that go into the same direction. So we have the RK star, but then we measured also many branching fractions as a function of the transferred momentum of the Q square. And also there we see deviations, all going into the same direction. So that there is a picture which is much more complex than two single measurements. And this makes it interesting. But of course, it can be, at this level, it can well be a statistical fluctuation. We'll see. I mean, we are waiting our colleagues to deliver the updated analysis with run-2 data, and this will give sort of, hopefully, a definite answer in either direction.
Other questions, please. Let me ask also questions.
Yes.
Have you a program for searching for charged scalar particles? Because it's very important for Higgs boson. If you have only one Higgs boson, as now we believe it's 1 point. But if you have two doublet Higgs models, for example, you have 3 extra scalar particles. So it's also have to be considered as an important program, because only one Higgs boson is such a mass which we have. Does not fit a lot of different experiments. For example, Sakharov conditions for baryogenesis and so on. So if we have, for example, 2 Higgs doublet standard model, due to charged scalar, it's possible to organize such type of processes. So have your program for searching for charged scalar?
So we are, in general, we are not very good at searches. Oh, I forgot my last slide. It appeared now. Okay. In general, we are not very good at searches because, first of all, we are running at low luminosity. So by simple cross-section considerations, we are not very sensitive. And indeed, although we could be able probably to see the Higgs, the standard Higgs into BB bar, for example, we don't expect enough events to be seen because we don't have cross-section, we don't have luminosity essentially. So if these particles have a cross-section at the level of the standard Higgs, then they are out of reach. However, we have, on the other hand, an interesting program on long-lived particles, massive particles, that include also some exotic Higgs, not specifically charged Higgs, but minimal supersymmetric Higgs, etc. Because this is an interesting program that we can do with our experiment. Yeah.
Thank you.
Welcome.
Other questions? Let's send speaker again. Next speaker is Valery Pugac, physics and techniques of the fixed metal microcrypts target at the LHCb experiment.
So good afternoon to everybody. First of all, I would like to thank organizing committee for organizing this nice and very important for us event. I would like to express the desire that it becomes regular, at least probably 2 times, in 2 years once. And then you understand what I mean, especially Ukrainian high energy physicists. This is the way how we see each other and how top rank people see us and decide whether we are worth it to give us money for continuing our studies or not. And I think that all what we shall hear today says that it is really the fact that high energy physics is at high level in Ukraine, and it is worthwhile to gather, evaluate it, and to see the perspective. Thank you again. And as Giovanni Pasoleva has told, LHCb experiment, I am working at the LHCb experiment. And I have a rather big group there. I am happy that there are many people who are not elder than 30 years. So the future upgrades, which were mentioned by Giovanni, also are for them. And I will present you what I am working on with my colleagues, also from other countries, on the physics and techniques of the fixed metal microstrip target for the LHCb experiment. This is already 1.5 years that we are discussing this, and now let me show what I'm going to talk about. This will be a small introduction, then physics about QCD and concerning the physics which we are going to see there, and also what is the physics which is used to govern by this special way, special target, and then how it will be realized, and then summary and outlook. So what is the reason? Why do we consider that it is important? First of all, the success of LHCb group, which has been partially presented, I mean the results have been partially presented by Giovanni, that in spite of the fact that LHCb detector has been designed for the flavor physics studies, for CP violation, it appeared to be that the detector is so beautiful that it allows detector by itself also to work with very high rates, with very high multiplicities, which are typical for the ion collision physics. And then there was a proposal, there was proposal by this group of people to participate, that LHCb participates in heavy ion physics, and it has been realized, as it was mentioned already, this mainly, it is realized exploring the noble gases, which are injected, and then there are collisions of ions with these gases, but this is limited to what? Helium, neon, argon, maybe xenon, and that's it. So what I am talking about, that we shall see that, first of all, there were, of course, very successful results obtained with collisions of heavy ions and measured by LHCb detectors, as it is shown here, and we are talking about so-called nuclear modification factor, which reflects what is the difference in the differential, these are differential cross sections, if we compare proton-proton scattering and, for instance, proton and lead scattering. This is the attempt to evaluate what is the effect of cold nuclear matter, what is the effect of hot nuclear matter, which is probably created in the status of the Pogleon plasma. And you can see here that if this will be the same, there will be no impact of the environment, then this ratio has to be close to unity. But what has been measured, for instance, in case of proton-lead collisions by LHCb detector is represented here as a function of rapidity and as a function of the momentum transferred. And you can see that there is a significant deviation from the unity, which is interpreted in terms of existing theories, but with very large uncertainties. Another measurement was in proton-lead collisions at 8 tera-electron volts. Previous was at 5 tera-electron volts, and here it is even more impressive difference of this distribution over transferred momentum. You see, it is twice less than it would be if there is no impact of this hot environment. And what is classical and beautiful feature of LHCb, that in the best way among other experiments in LHC, it can measure the production from the primary vertices and from the secondary vertices. The resolution of vertex locator, which is the best in the world, allows to separate the production, for instance, of J psi's from the primary interactions, where we could expect hot environment impact, and from B species, which live 10 to minus 12 nanoseconds, 10 to minus 12 seconds, and is decaying far away from this hot environment. So there has to be nothing which changes, and it is really what is observed. We see that the points, experimental points, are very close to unity for these species which are far away from the interaction region, and there is strong impact when it is in the close vicinity to the primary vertices. So this is the physics reasons why we have decided, why don't we consider the expansion of the fixed target nuclei, which could be started by LHCb. So if we go to metal targets, then in comparison with this only, as I mentioned, noble gases, we shall have immense variety of colliding nuclei, and this will enrich LHC physics tasks. This is in search for signatures of Pogleon plasma. There could be possible dependence on ground state properties of colliding nuclei. Even it sounds a little bit probably surprising how it could be, but this is how physics, experimental physics performs. You do not expect, but the nature shows to you that you have to take it into account. What are properties of the ground state of colliding nuclei? Then nuclear and probably even atomic dependence of the quark-quarkonia production including also if there could be n interaction points. I shall, here I just wanted to show you from the table of elements how big will be the targets region if we go to metals. These are shown in this blue color. And then even if now we have a lot of data produced in PP and P-lead or P-neon, P-helium, and lead collisions and goals, this is large, of course, sample of data, but still limited range of the knowledge about the impact of the initial state on nucleus-nucleus interactions. I mean, what could be important? Important could be the properties of the ground states, including parity, spin, then dependence upon the isotopes, spin and parity, deformation of nuclei, closed shells, impact, and neutron skin. For instance, it is well known that nuclei could be in different shapes already in the ground states. Whether it will be the same if we collide them, spherical nuclei and deformed nuclei, this has to be tested. This has to be, one can say it is not important because this is the wavelength is so small that we feel only nuclear-nuclear interactions. But this is our assumption. And whether this is true or not, this has to be tested. And just to give you a little bit of relaxation, this is really bullet interacting with different targets, and you see that the interaction could be different. It's really photos. Now, and be a little bit more serious, from the point of view of relativistic collisions, building such fixed target regime at LHC will allow to bridge the gap which has been already studied at SPS and Large Hadron Collider, and then this phase diagram, we shall go to this very dense matter, while now we make at LHC experiments very hot matter studies, and this is approximately what we expect at the neutron stars. Okay, so this picture shows that how we can expect different results of interaction of nuclei in metal nuclei. That there could be impact, as I said, of charge polarization and primary excitation of nuclei, giant resonances could be created, and so on. And neutron excess may create even neutron nuclei. There were some publications on that theme. And this is what I see that absolutely never exploited picture, that if we have crystalline target and we hit it by a proton, then it is kind of chain reaction. And then one could expect here that we can see by our detectors on periphery some impact of this. And depending upon the orientation of this crystal axis, we shall see different results. So coming back to the LHCb experiment, I will not go into the details, but this is excellent detector, which for few of characteristics is the best in the world. And this has to be exploited, I think, in more details than before. And why do we start with this? Because many years ago, many of people who are present here were also participating in Harabi experiment more than 20 years ago. And there, as you see, the structure of Harabi and LHCb very similar. And that is why I have, and this is how it started, our participation in LHCb in 1994 in the letter of intent. And you can see here the group of Institute for Nuclear Research, the group from Institute of Physics and Techniques in Kharkiv, participating in LHCb from the very beginning. From the very beginning, we were participating in the building silicon tracker especially inner tracker. And the first microstrip detectors at LHCb were made in Ukraine, by the way. And these were prototypes which were used later for ordering mass production by Hamamatsu. So LHCb experiment acceptance for the fixed target is very well suited. We shall have central events monitored. And in fixed target regime at LHCb, as I mentioned, we shall go to the studies of, for instance, one of the observables like nuclear modification factors. We shall look into the differential cross-sections dependence upon rapidity, upon the momentum transfer, compare it with theoretical conditions, and make a decision about the physics which is under, which is behind this. So how it is proposed to make? Like in Herabi case, we, at first with my colleagues from many institutes, we have decided, why don't we make the target like it was in Herabi case? That means that we make wire target which approaches the hollow of the beam, and then measuring the current which is induced by interaction of, let us say, ions and metal nuclei, we shall see the luminosity which is shown here, and in this way we can monitor. For evaluation of this proposal, there is fixed target panel of LHCb, which includes, for instance, Giovanni Pasaleva and former spokesperson Guy Wilkinson, and they have evaluated this as well as others' proposal for fixed targets, and they have made some proposals which are shown here. We have taken this into account, and the main principle which is shown here, the physics, how it works. I mean, the determination of luminosity, the steer, and so on. This is a thin target, could be few micrometers only, but the secondary electron emission under the impact of charged particles is such that emission occurs at very thin surface layers, few nanometers only. And then when these secondary electrons are emitted, the isolated foil will be positively charged. And we measure this positive charge by our special built charge integrators built in collaboration with Max Planck Institute of Physics in Heidelberg and our Institute for Nuclear Research. And this is the picture which we have measured in Herabi, which demonstrates how perfect is performance of such approach, that if we insert, for instance, different targets simultaneously in the beam, in one experiment we have 8 interaction points, 8 nucleus measured, and this allows to exclude many systematic errors of experiment. So this is how it is checked by, we make equalization of contributions of interactions by our method, measuring charge, which I have shown there, and then reconstruction of vertices by vertex detectors has shown that it works. The principle is correct, and it allows to distribute equally the luminosity over inserted targets. But for that, of course, one needs group. And this is the group as far as we are talking also about 100th anniversary of our Academy of Sciences. This includes also our people from Institute for Nuclear Research and Dortmund University. And this was a big group. The activity of which was devoted completely to the operation of the target. This is how it has to be, Giovanni, probably organized, if it will be approved, also at LHCb. There has to be about 8-10 persons who will run this, who will build and run the system. And physics results from Herabi case that we were really able to measure, to get interesting results about for instance, here, nuclear dependence of J psi production at Hera B. This our experimental points as function of XF Fermi variable, and these are different theories. And you see that the data allows to get, first of all, very precise results, but secondly, to separate between different theories. Now, LHC experts were against, were against our proposal. Why? Because they considered that this is very dangerous and it may lead to quench of the superconductive methods. Then I was advised by FITPEN members that I have to discuss this with LHC experts seriously in details, and I have 50 letters, about 50 letters of discussions, and 3 weeks ago I have had also personal meetings with them, and I have managed to persuade the experts that if we go from the wire target working in the hollow of the beam to the very super thin target, which could be even inserted in the core beam, and formulate the condition that produced luminosity will never exceed the luminosity which is produced, for instance, in PP collisions, then it is not dangerous. And LHC experts has accepted this and even proposed how we can start and work. For that, we propose to explore our super thin metal microstrip detectors as targets. The original technology patented already in Kiev allows to build special detectors. About 1,000 strips already now we can build, and this can be inserted later into the into the beam. As I said, even in the core of the beam. This is the structure of the vertex locator detector, and this is also a picture which shows where we propose to insert these stations and how to build it using one of the stations of existing stations. And this has to be connected to the nanometer actuator. And this is getting to be discussed within the Velo group. And we think that we can persuade them. And this is how it will be done. This is our detector, which is produced in Kiev, and it is. I am happy to underline that this is possible only at Kiev production of this super thin detectors with 1 micrometer thickness and up to 1 micrometer pitch. And we have applied this at many places. This will be reported by Alexei Kovalchuk a little bit. This is a photo of such 1024 strips, and this is how it will be operated in the beam. This is the beam, and we insert it by a mechanical actuator, and then we also allow to go we allow the current to come through the strips, and if luminosity becomes dangerous, we send pulse of the current and we burn out this target. So it's internally, I say, safe to operation. So this is currently, Sergei Kaliev will tell us about operation of radiation monitoring system, which is existing, which is under operation currently, and we are going to use just the same data acquisition system for operating this strip detector, as I told. Just for relaxing and for theoreticians, what could be made unusual with such target? If we insert our target and we allow, let us say, lead target, and we allow 2 beams come to it, what happens? Can you answer me? This will be a system of 600, more than 600 nucleons. And what will be properties of this system? And it has not ever been even discussed. And such target setup allows to approach this unusual scene, and I find it very exciting. So I will skip the details. this is our group, which is from high energy physics department in Kyiv, which could contribute into the development of such target setup. And to summarize, I could say that there are good physical and technical reasons to build the metal microstrip fixed target setup at LHCb, and Kin Group will contribute by designing and building this super thin wire target setup. The super thin wire target is, of course, challenging project, but we shall search for the way to overcome the challenges. In realization, if not excluded, even it is not excluded that target arrives into the beam. It is also getting status of the primary object of the LHC beam, and it is not dangerous. One has to just work out the safe mode of operation of this complex setup. This project, metal microstrip detector as target in LHC beam, is under development at Kyiv Institute for Nuclear Research. We are welcome to join this activity. And it was more than one time in the experimental physics that what looked impossible yesterday was solved today. And major sense in this activity, I see that this is the chance to discover new physics events with such targets. So these are acknowledgements, and thank you for your attention.
Thank you. We have time for one question. No question. Oh, you, please.
I have a very technical question. What are the main challenges or technical challenges in microstrip detector usage? And what is it? Yeah. Do you need some physics behind this, electromagnetics or whatever?
Yeah. What is the challenge? Technical challenge, you mean, or physical?
Okay, physical.
Physical.
Yeah.
Yeah, just as I have shown just a few slides before, 3 nucleus collisions.
No. I mean, what you are expecting from this very particular microstrip detector, not any others.
You see, currently, LHCb is the only one experiment in LHC which performs experiments in fixed target. And we are limited to very few nuclei: neon, helium, and argon, maybe xenon. That's it.
Okay, thank you. Understood. Thank you.
Thank you. We have no time for. Thank you very much for our speakers, because we have the time. Next speaker is Valeria Zhukovskaya, CERN-UA production via hadronic decays. 20 minutes.
So, good afternoon. Today I would like to discuss CERN-UA production via hadronic decays in LHCb experiment. So, CERN-UA is a bound state of CC bar pair, where J psi and psi2s states can be reconstructed via clean channel, d-muon channel. Some other states like that can be studied via their radiative decay to J psi. To study other CERN-UA states, it is very important to study them through hadronic decays. So the first attempt to describe J psi production at Tevatron led to creation of J psi CERN-UA puzzle. Later added J psi polarization and eta C1s production measurements required of theoretical model extensions. So at the present moment, comprehensive model of heavy flavor production still not completed, but it may be solved by adding more precise measurements or new sources of input. So at the present moment, the most powerful tool to describe CERN-UA and quark-UA production is non-relativistic QCD. It has 3 measure assumptions. The first of them says that quark-UA production process can be factorized on short distance hard QQ bar pair formation, and software scale hadronization described by long distance matrix element. In addition to color singlet model, which assumes the same quantum numbers for QQ bar pair and final state, the color octet model allows them to have different quantum numbers, and it can be corrected by subgluon emitting. So within the universality assumption, the same long-distance matrix elements expected for hadron production and production of Charmonia in BD case. When heavy quark spin symmetry assumptions say that long-distance matrix elements for color singlet and color octet of different quark-quantum states are linked between. So describing of J-psi production measurement at LHCb expects dominant color octet contribution, and from that assumption, it expects J-psi to be strongly polarized at high PT. However, measurement of J-psi polarization does not agree with this statement, and therefore requires large color singlet contribution. And since known heavy quark spin symmetry relations between long-distance matrix elements, a few different theoretical groups performed fit to eta-C production. And contrary to theoretical expectations, there is color octet and blue band is color singlet. The data was entirely described by color singlet contribution. And using the eta-C production measurements, it appeared to be possible to make the constraint for one of color octet long-distance matrix element. And so using this measurement, new constraints on J-psi polarization have been performed. But still, these results have some tensions with CDF data and hierarchy problem due to cancellation between two large color octet matrix elements. But it may be solved, including some model extensions, such as soft gluon fragmentation, or by simultaneous study of hadron production and production in BD case of different Charmonia states. And also, this is very interesting to perform the same study for eta-C to S and psi to S states due to clean interpretation, since no feed down from higher Charmonia states. So, and now the LHCb detector, as was mentioned before, is single arm forward spectrometer designed for flavor physics studying. Despite just 4% of solid angle coverage, it receives up to 40% of heavy quarkonia production cross-section. It performs complementary cross-section measurements and overlap with other LHC experiments in range of rapidity. And due to high performance of vertex locator and two ring imaging Cherenkov counters, it allows to perform study of quarkonia states decays through hadronic final states. So microstrip silicon vertex locator located as close as 8 millimeter from interaction point performs excellent track reconstruction, impact parameter measurements, and reconstruction of heavy flavor decay vertices to study B hadron decays. Charged hadron identification is performed by two ring imaging Cherenkov detectors with 3 radiators, which cover wide solid angle and momenta phase space, and by hybrid photon detector to collect Cherenkov light. And charged hadron identification is illustrated by this plot, where blue line indicates invariant mass of 2-pi combination. And using RICH, it can be disentangled to many different B hadron decays, which are very important for CP violation studying. So Charmonia prompt production and production in B decays can be studied through different hadronic final stages, such as PP bar and 5-5, and can be distinguished via pseudo-proper decay time restriction or fit to its variable. And the first measurement of eta C1s production and 7 and 8 TV have been performed by LHCb experiment and shown below. And as was mentioned before, this measurement had strong impact on theoretical predictions of heavy flavor production. And there is the same measurement for 13 TV center of mass energy, and where from simultaneous likelihood fit to pp bar invariant mass in bins of PT and TZ is shown there. We extracted Charmonier yields to use them in simultaneous integral chi-square TZ fit in bins of PT. And from that fit, we separated prompt Charmonier and Charmonier from BDKs. And projection on one of PT bins of TZ feed is shown there for J psi and eta C. And red line illustrates prompt production, green line illustrates production in BDKs. Differential production cross-section is shown on the top of slide. And integrated over the range of LHCb acceptance, production cross-section and relative branching ratio are calculated for this analysis. And the value in blue is circled on a plot to show you production cross-section of eta C dependence on LHC energy there. And so using known relation between long-distance matrix elements and calculated branching ratios, theoretical fits have been performed for different long-distance matrix elements. And comparison between fit, which uses only relative branching ratio and including J psi production in BDKs are shown below. And color axis indicates quality of fit. So on this slide, in left column, you can see results of fit to pairs of different long-distance matrix elements. The right column illustrates the same fits performed for a difference between the same long-distance matrix elements, defined from production in BDKs and from Hadra production. These fits are very important to validate factorization and universality assumption of NRQCD, and understanding of theoretical uncertainties included in this fit is very important to compare experimental results and theoretical predictions. So the technique of 2D fit to invariant mass of 5π in bins of invariant mass of 5π allows to reconstruct invariant mass spectra of true 5π combinations. And using this result, the first measurement of chi-C0 production in B hadron decays have been performed, as well as the most precise measurement of chi-C1 and chi-C2 states in BDKs was measured at LHCb. And so using this result and relation between long-distance matrix elements, two different theoretical fits have been performed. The last one demonstrates fit to 3 measurement of branching fractions, and it allows to constrain phase space of these long-distance matrix elements. The second fit performed for the ratio between branching ratios, and this fit demonstrates a problem of theoretical description of eta C production, of chi-C production. So in order to improve theoretical models, it is very important to understand sources of theoretical uncertainties. And it may be done including higher order calculations, as well as simultaneous study of Hadra production of Charmonier and Charmonier production in BDKs for different Charmonier states. And alternatively, once Hadra production and production in BDKs measured for Charmonium states with linked long-distance matrix elements, the above assumptions can be tested quantitatively. And so using the same technique as for Chi-C production, the eta-C2S production in BDKs have been measured at the first time. And it is very important to perform the same measurement for eta-C2S hydro production. And in order to do this, a dedicated trigger line will be used in 2018 data collection. And so as a product of analysis and using 3D fit to K plus K minus invariant mass, the first evidence of B-sub-S to 3-phi decay have been seen in LHCb, and its invariant mass spectra was placed at the cover page of European Physics Journal. And so using this formula and values calculated in the previous analysis, the ratio for eta-C to 5-phi to eta-C to pp bar branching ratios was calculated, and its value larger than value determined from pedicle data group. And in summary, it's important to say that comprehensive model of heavy flavor production is still not completed. Nevertheless, LHCb has crucial impact on validation of QCD and its constraining by simultaneous study of Charmonia hydro production and production in BDKs. And Chi-C and eta-C2S production in BDKs have been measured yet and have important application. And for further theoretical models improvement, it is possible to include measurements of HC and eta-C2S production, as well as Charmonia decays to other final states. So thank you for your attention.
Please, questions, if you have. Is it possible to mention at least which kind of theoretical uncertainties you mean in your talk? About what kind of theoretical uncertainties you say in your talk? Because you like theoretical your final slide, please. Summary.
Yeah, I understand, but
okay, good.
These plots demonstrate that fits which includes. So we can define these matrix elements using theoretical predictions only, and we can define them from fit to production of different Charmonia states. So the first way assumes to include theoretical uncertainties. The second way assumes to have only impact of experimental result.
Thank you. Thank you. Other questions? No? No. Let us thank speaker again. Okay, we have to be hurry. Next speaker, Vasil Dibashuk, GPC production in PP ultra-ferric Hall. Collisions at 5 GeV in the LHCb experiment. 20 minutes, sorry.
Okay, good afternoon. I understand that everybody is tired, but anyway, I would like to introduce the study on the JPSI production in lead-lead ultraperipheral collisions at 5 TeV in the LHCb experiment. Why it's important? Because this analysis is the first LHCb analysis for the lead collisions. So that gives this analysis show the real potential of the LHCb experiment in comparison with CMS, ALICE, and ATLAS experiment at CERN. So my talk, the outline of my talk is here. Basically, I will try to make some to talk about some basics of UPC physics, give the physics goals in such realm of physics, give the present status of UPC physics, and move to the role of the LHCb experiment and in particular in such analysis and some conclusions. So ultraperipheral collisions, this is the reaction in which the colliding nuclei do not physically collide, but they interact via low-range electromagnetic force through the virtual photons that come from the electromagnetic field that surround the fast-moving charged particles. And from the theory, we know that the intensity of such electromagnetic field is proportional to this z squared, that is the charge particle squared, and we have we benefit from this feature for in lead-lead collisions. So, frankly speaking, the ultraperipheral collisions is not similar with conventional hadronic collisions, because here we expect only the particles on which our mesons that is produced via photonuclear interaction produce. So from the theory, we know that such collisions occur when the impact parameter is larger than the sum of two colliding nuclei. So in principle, experimentalists do not measure such parameter, but in return, we can measure the particle multiplicity. So it's the first main chief feature of UPC collisions that help physicists to separate the potential candidates for such events. Also, there is some similarity for the deep inelastic scattering, but here we consider the very low, almost zero photon virtuality. So what is the mechanism of photoproduction, of vector meson production in ultraperipheral collisions? Here you see two mechanisms, where the first one is the coherent production, where the emitted photon can fluctuate to the quark-antiquark pairs that then can scatter from the whole nuclei, from the whole nucleus, and in such case we have the low transverse momentum. For example, for the incoherent production, the transverse momentum is higher. So this is the second experimental signature to separate, to distinguish coherent production from incoherent production. So for the present analysis, coherent production is a signal process. So what is physics motivation? From the theory, we know that the perturbative quantum chromodynamics can predict the cross-section for such vector meson production. But the main interest of vector meson production at hadron colliders is the direct determination of gluon distribution in nucleus and nuclei. Why? Because as we know, gluons do not carry any charge. So only in such photoproduction, photonuclear interaction, we can probe the inner structure of nuclei. So, and of course, we can, or theorists can make some predictions on the gluon saturation effect at low Birken X values. So, as you may pay attention that often talk about the photons. Of course, photons can be treated as a perfect probes for the precision measurements of inner structure of nuclei. So, for example, in 19th at Hera, for example, H1 and Zeus experiment explored the structure in the structure of protons at very low Birken X values down to 10 to -5, a different center of mass energy. But then the experiments like Star, Phoenix, and CDF at RIC explored the vector meson production at heavy ion collision, first heavy ion collision, for example, our collisions. And now the LHCb experiments play the leading role in such high energy photo-mediated interaction because they open a new kinematic space that is extend the energy in the photon nuclear center of mass energy up to 3 TeV and down to 10 to -6 at Birken X values. So this figure show you the microscope that high energy physicists in LHCb experiment use to investigate UPC physics. And as was mentioned before, there are a lot of advances of the structure of LHCb detector. The main purpose, the main advantages pros the high muon identification and high mass invariant mass resolution. So for the UPC physics, the most relevant part of the LHCb detector is the vertex locator and the tracking station, and also the muon station, where we expect the presence of hits from the tracks from two tracks produced by muons. So really, LHCb experiment is very suitable for such studies because it fully instrumented as its tracking, calorimetry, and particle identification pseudo-rapidity in the pseudo-rapidity acceptance. And such pseudo-rapidity range can be extended to the values ±10 via using the Herschel detector that consists of 5 scintillator stations that can which we can use as a veto to veto the remnants or emitted neutrons during the photonuclear interactions. So also LHCb experiment has lower average pile-up in comparison with ELISE, ATLAS, and CMS experiment. So what is the strategy of our analysis? So we required the presence of only 2 muons. So we expect only 2 long tracks in the detector acceptance. And we performed 2 steps to extract the signal candidates of GPSI. So the first step is the invariant mass feed where you can see the very poor invariant mass spectrum of J-psi and psi-2s even peaks. So we required such cut for the track muon track's momentum, and apply such invariant mass window. So the next step is to analyze the squared transverse momentum distribution of our candidates. So for that purpose, we used the Starlight, that is the special Monte Carlo generator focused on mainly on the physics for LHCb and RIG colliders. So we take from this generator several templates, for example, for coherent, for poor electromagnetic interaction, and incoherent, to produce the fit of experimental data. So here you can see the uncertainties table of general uncertainties, and the main contribution comes from the luminosity determination. It's up to 30%. So, and here it's the first preliminary public result of coherent J-psi production in the LHCb experiment at 5 TeV. I can say that this result was presented yesterday at Quark Matter 2014 in Venezia, Italy. So it really gives the ground for the theorists to move forward and give their predictions for such physics. So to conclude, I would like to say that LHCb has a large potential for studying the photoproduction in heavy ion collisions, and it was presented the first measurement of coherent J-psi production, that collision with the LHCb experiment, and we can one can see that a good agreement of the coherent J-psi production with several perturbative QCD and colored dipole models. So we are also planning to improve our efficiency determination for the publication, and of course also calculate the ratio of coherent psi-2s and to J-psi cross-section, and include the data from Herschel detector to extend maybe this analysis to the exclusive coherent J-psi production. So, and here I would like to acknowledge many people without whom my participation would have not been possible in this analysis. Thank you very much.
Questions, please. Please.
Ask you a few words about theoretical models which you use to compare with your data. So you mentioned perturbative QCD.
Yes.
Can you just say a few words what precisely you mean by this? I mean, what kind of diagrams are included, etc.?
Frankly speaking, not to my knowledge, because I would say that the perturbative QCD models provide some prediction for such coherent J-psi production because of the high mass of J-psi meson. So even if we have the low photon virtuality almost zero, but the high mass of GPSI meson give us possibility to make some perturbative prediction from perturbative chromodynamics. It's, as I understand.
Other questions, please. I have a very short questions.
Yeah.
You said long range electromagnetic forces. What does it mean, long range electromagnetic forces? It seems to me that all electromagnetic forces are long range. On your talk, you mentioned long range electromagnetic forces.
But what is
this?
Yes, really, we know that there is a short range force, like a strong.
You mean interaction in the long is very low frequencies?
No.
What is long range electromagnetic force? What does it mean?
That means that the interaction can be possible at distances that exceed the size of nucleus. So even if we do not have nuclear overlap, there is interaction via electromagnetic.
Okay, thank you.
Okay.
Thank you. Let us thank you again. And our last speaker, Volodymyr Kotlyar.
Калиев.
Извиняюсь, я пропустил, да. Калиев, да. Radiation. Это я спешу. Sorry. Radiation monitoring system for LHCb in 2070 year. Sorry.
Hi, I am Sergey, and I am PhD student from Institute for Nuclear Research in Kiev. And my topic is radiation monitoring system in LHCb in 2017 years.
Это не то. Нет, то на втором экране. Здесь сработало, или нет? Еще.
Okay. And in this picture, you can see detector system LHCb experiment, and radiation monitoring system is located here. It's before tracking system 2, and main goal radiation monitoring system is measurement radiation loads to the inner tracker. In this slide, you can see silicon sensors, and here is interaction point, and before the silicon sensors located radiation monitoring system. And here you can see main characteristics for inner tracker. The RMS is based on the metal foil detector technology development in Kiev, and the RMS detection part comprise 4 boxes. You can see tube when go beam, and around tube you can see 4 models. This is RMS models, and one RMS models has 7 sensors. Dimensions of sensors are close to inner tracker ones, and the main function to monitor radiation load on silicon tracker sensors. Metal foil detector is a metal foil connected to the sensitive charge integrator. Is here charge integrator, and the principle operation, secondary electron emission from metal foil surface from 10 to 15 nanometers, caused by projectile charge particles. Positive charge created in metal foil is integrated by charge integrator, conversion it into a frequency measured by a scalar. The calibration current at the input of the charge integrators is set to 215 picoamperes, determines a baseline of 22 to 25 kilohertz for output frequency 10 femtocoulomb in one count. One count in the charge integrator is generated by 10 to 4 charge particles hitting sensor per second, and linear response up to 1 megahertz output frequency. In this form, you can see how we take the data. In the vertical axis, we have frequency, and for the horizontal axis, we have time. Blue line is regime when no beam, and red line is regime when we have particle collisions. And in the bottom pictures, you can see how many counts has regime physics, it's red, and how many counts have regime no beam. After, when we download data, we can calculate fluence and have distributions for all sensors. Fluence we calculate with this formula. We have, we must minus counts from the regime physics minus regime no beam, and multiply to the time when we have field, and divide to the sensor area. And this corresponds to the 3.5 to 10 to 12 MIP to centimeter square over silicon sensors of the interaction 2 station. After we can calculate those loads to the all sensors, is those inscribed to the all years. And the silicon sensors of the IT2 have absorbed to 1 kilogram for 2017 years. And we can calculate leakage current and have distributions to the all sensors. And the leakage current throws C sensors of IT2 have inscribed by 300 microampere, depending on the sensor size and position. Sorry. In this slide, we can see how we can see distributions for the luminosity. We calculated, we calibration data from radiation monitoring system and have value to luminosity for the all years. And in the top pictures, it's long sensors data, and in the bottom pictures, it's data from short sensors. RMS, together with beam loss scintillations and beam condition monitor, is displayed at beam and background panel in the control room. This panel is very essential during beam injection to prevent radiation damage of the detectors, and this screen is from control room, experiment LHCb. These pictures illustrated how we can calibrations of RMS from luminosity, and measurement was made. This allowed to extrapolate RMS data fluence on non-detected by RMS fields. These pictures illustrated evolution of the delivered luminosity at LHCb measurement by RMS in comparison with LHCb data. And conclusions, RMS data allows to measure charged particles fluence over IT silicon sensors, and RMS is used as beam and background tools to monitor radiation background, very important during beam injections to avoid radiation damage. And RMS is applied to measure instantaneous and integrate luminosity. And many thanks all people in LHCb and ST group for his help in RMS installation and commissions. And many thanks to Gloria Corti to help with background simulations and RMS respond on it. Thank you.
Thank you. Any questions, please? There are no questions. Thank you again. And the last talk is Volodymyr Kotlyar, Mechanisms of Open Charm and Beauty Production as the LHC Energies.
Thanks. Needless to say that open charm and beauty productions are studied very intensively, not only zirconium and onium production, but these processes also are in the focus of experimental and theoretical investigations. These processes are studied to test prediction of perturbative quantum chromodynamics. This means to test different approaches and methods how to calculate the amplitudes and cross sections. Then to study the fragmentation functions. This function cannot be described in perturbative basis, and usually they have phenomenological grounds. When the mechanism of these processes is under control, comparison with experimental data can be used to learn something about pattern distribution functions. In particular, about gluon distributions in protons and nuclei and quark distributions. Here it should be noted that gluon distributions in protons and nuclei are hardly possible to study in electron-proton or electron-nucleus collisions. In those electromagnetic processes, contributions from gluon distributions appear only in high orders, while in hadronic processes, like in scattering of protons or nuclei, initial states with pair of gluons are in the leading order. So it is a great advantage of such processes to study this complicated and intriguing gluon dynamics. Of course, observations and calculations in proton-proton collisions are a reference point to study, in general, small effects when collisions of atomic nuclei is studied, with the aim to know something about the extension of standard model or properties of quark-gluon matter. Our aim here is to calculate the cross sections, integral and differential cross sections of the processes, those charm quark, D-meson, or charmed baryons are produced in respectively with processes where big quarks, B-meson, or beauty baryons are produced under conditions of the LHC experiments. Our emphasis is on the low PT region, where measurements are performed by ELIS and LHCb. ELIS studies the central region in rapidities, while LHCb, as we see today, is studying the forward rapidity regions. At the same time, in the gas target experiments, due to boost, the forward rapidity region of detector will be boosted or shifted into the central region. So in the gas target experiments, LHCb and UA9 will study central rapidity region like ELIS in the proton-proton collisions. Here, some processes that we include in the calculations are listed. We consider reading order, then add some light jets in the final states, and here number of processes involved is demonstrated. This number is growing dramatically. Next line consists the sum of is the sum of previous ones. So this line consists number which is in leading order. Since we would like to compare this experimental data on charm production, we use a model with massive C quarks. In this case, proton consists of gluons, up, down, and strange quarks. There are no C or B quarks inside the proton in such calculations. In the region of high PT studies, it's possible to use a model with massless C quarks when it's physically motivated. In that case, C quarks can be included into the proton and corresponding distributions can be investigated. In the upper part of the figure, processes are for the calculations in tree approximation. In the lower part, both real and virtual particle emissions are included. Here, each line corresponds to this group of processes, and some is not shown. Since the number of processes or diagrams is rather large, all this can be computed with computing tools. And here is results for production of pair C quarks, 1 pair, 2 pairs, and 3 pairs. It seems that production of 2 pairs and 3 pairs are strongly suppressed. So this means that studying of correlations in this case is not an easy task due to small value of integral cross-section. This is results for energy of gas target experiments for proton collisions when one proton is beam and another proton is in target. Here is corrections due to emission of jets that are produced by light quarks and gluons. This again tree approximation, and we show how cross-section changes when we add particles in the final state. Now we perform calculations with more than 5 particles in the final state. They are not shown here, but tendency is the same. And at last, here are results for calculations with loops, where real and virtual emission is taken into account. Here, number of processes is slightly restricted by computing time, but we see that processes of high order bring smaller and smaller contribution. And this is nice. In previous slide, we see that cross-section go down slowly. Here are shown also the theoretical uncertainties. These uncertainties originate from variations by variations of renormalization and factorization scales. In complete calculations, the result should not depend on these variations. But in real calculations, these variations are rather strong, and here a typical range of variation envelope from 1/2, 1, and 2 is used to see the variations. We can see that difference between the values of cross sections are smaller or even less than these variations. And this is a big problem, a big challenge for these low PT region calculations. These are results for integral cross sections, for beam gas target experiments, for charm baryon production. Pair of these dots means upper point is for the whole kinematic region, and then next dot is corresponds to acceptance of the detector. This is region in rapidities which can be measured in this experiment. We see that cross-section of charm baryons strongly decreases with these baryons. This means that it wasn't an easy task to measure these baryons. At least it's hardly possible to think that correlations here could be studied. Next, beauty production. Again, we show the number of processes included in the calculations, entry and real and virtual emissions. Here, big quarks are massive. Proton consists of up, down, S and C massless quarks and gluons, of course. In tree approximation, we have the following integral cross-section for the big quark production at this energy. Again, we see that there is something like saturation here when we add light jet in the final state, and might be it could be observed here with loop calculations. Here we compare predictions used with MATGRAPH. We use MATGRAPH and PFA8 for these calculations with experimental point obtained by LHCb collaboration. The theoretical uncertainties due to scale variations are so big, so it's hardly to decide whether there is an agreement with experiment or not. These uncertainties are rather big. In its turn, uncertainties due to Parton distribution functions are much smaller, and they are not very essential here. In this context, it should be also might be noted that when it is awfully said that standard model, in particular chromodynamics, is in agreement with experimental data, this is an explanation. What means this correspondence? This is correspondence within theoretical uncertainties. This is a comparison with LHCb experimental data for big quark production. LHCb has measured might be everything what can be obtained from the big quark, and so fragmentation functions are eliminated, and we can compare really observables for big quark production. Next, B plus meson production. Here again we see LHCb data, and this data compared with MATGRAPH and PFA8 predictions. we see that experimental uncertainties are much smaller than theoretical ones. And in many cases, this is a typical situation for the experiments at LHCb. Here we compare forward region with central region. This is prediction for Alice conditions. And this is point of CMS acceptance. In CMS acceptance, there is a cutoff on lower peaky region. It's quite different kinematical region. Due to this cutoff, we have small variations here in theory. This is a distribution for B plus production and comparison with LHCb data. Here, central value obtained in calculations are rather close to the experimental point. And last, we would like to compare results for the top quark production recently presented by the LHCb quite recently in this paper, and predictions with MATGRAPH. We have seen this point today already, but experimental point was to the right from the theoretical predictions. It's hardly possible to say what the calculations used to compare with this experimental point. Might be this is calculations of this type. But when we add additional jets in the final state in 3 calculations, we see that we get not only this point, this is leading order, but this point and this point. So experimental data is within the range of theoretical variations. These calculations are more consistent with inclusions of real and virtual particle production. These calculations are well below the experimental data. Our aim was to perform calculations under the conditions of LHCb and Alice, and to demonstrate how this result depends on some features of perturbative QCD. It might be seen that it is not a very straightforward story. And what I would like to say in conclusion, that we plan and hope to continue these studies and to perform theoretical analysis of various correlations in production of charm and beauty. Charm and beauty particles with light jets and with vector bosons. Thanks.
Thank you. Please, questions, if you have. Yes, I have one question of general type. You see, as a corollary of your talk, you see that theory is not in not a good position compared to the experiment. So very big uncertainties, and there are 2 questions arise. First is that what is the input in this program which presents itself as maybe it is QCD in some order, but how to succeed this program? Maybe it's necessary to apply some duality relations. Nowadays, it is very popular, even in thermodynamics on the lattices. We calculate not some QCD perturbatively, but some loops, some integral variables which sum up. For example, Maldo-Stena conjunction is just if we calculate a special type of diagrams in supersymmetric models. So it's unclear what is the theoretical perturbative input here. And among well, then other maybe it's necessary to do some recalculations, renormalization. It depends on the choice of this point. Okay, but which kinds of transformation have been done? Could you answer for these questions?
As for input, this is straightforward PQCD calculations, just performed with computer without any simplification. This is attractive feature to see what perturbative QCD can produce. Of course, effective theories are of great interest, but this is just only QCD, nothing more, and pattern distribution functions. When we treat hadrons, B-meson, or baryons, we need fragmentation functions, and that's all. As for scale dependence, the only way what can be seen at least now, up to my understanding, is to go to the high PT region, or to the region when heavy particles are produced like T-clock. With this large amount of energy in the final state, this dependence will be suppressed. But we would like to consider just opposite region. It's low PT region of ELISA and LHCb, with PT down to 1, GV over C or even 0, and not very heavy particles in the final state. So we meet with these problems.
Thank you. We have to close. You have a question? Please.
You write that you can study the gluon and quark distributions in a proton. Okay. As far as I understand, there is a very important part for the calculation of the PGFs, okay, of the proton. Haven't you checked whether your results have modified or corrected the well-known PDFs such as NNPDF, MasterWeb PDF, etc.?
Of course, we use most advanced models of pattern distribution function, such as neural networks, collaboration, CTEC, and some others. These calculations are supported with CERN-UA and
Do not they modify these distributions as well? Don't your results modify these distributions? So you just okay, thank you. Okay, thank you.
One second, one small announcement, please. Yes. I will repeat it in the end of our session. So, okay. We will provide tomorrow the bus which bring you to the Kharkiv Institute of Physics and Technology. So the bus start from the Hotel Mir and 8:15, and it also will be a short stop here near our institute. And after the, 1 second, sorry, at 9 o'clock I will remove it. It will be in our destination, and at the end of the session, the bus will transfer you from the institute to the Hotel Mir. Thank you, and I will repeat it in the end of our final session. All right. Stop.